Programming a guessing game. Let's jump into Rust by working through a hands-on project together. This chapter introduces you to a few common Rust concepts by showing you how to use them in a real program. You will learn about let match method, associated functions using external crates, and more. Okay. In the following chapters, we will explore these ideas in more detail. In this chapter, you will practice the fundamentals. We will implement a classic beginner programming problem, a guessing game. Here's how it works. The program will generate a random integer between 1 and 100. It will then prompt the player to enter a guess. After a guess is entered, the program will indicate whether the guess is too low or too high. The guess is correct. If the guess is correct, the game will print a congratulatory message and exit. Note, there are no quizzes in this chapter since it is just supposed to give you a feel for the language. Setting up a new project. To set up a new project, go to the project directory that you created in chapter 1 and make a new project using cargo new guessing game, cd guessing game. The first command cargo new takes the name of the project guessing game as the first argument. The second command changes to the new project directory. Look at generated cargo.toml file name cargo.toml. As you saw in chapter 1, cargo new generates a hello world, a program for you. Check out the src main.rs file. Generates a hello world program for you. Check out the now let's compile this hello world program and run it in the same step using the cargo run command. The run command comes in handy when you need to rapidly iterate on a project, as we will do in this game, quickly testing each iteration before moving on to the next one. Reopen the src/main.rs file. You will be writing all the code in this file. The run command comes in handy when you need to rapidly iterate on a project, as we will do in this game, quickly testing each iteration before moving on to the next one. Processing a guess. The first part of the guessing game program will ask you for your user input. Process that input and check that the input is in the expected form. To start, we will allow the player to input a guess. Enter the code in listing 2-1 intro src/main.rs file name src main.rs. So start, we allow to input a guess, enter the code in listing. Okay, so main function and println guess. Okay, and then mutable guess and string new and int to do as in. Okay, so this code contains a lot of information, so let's go over it line by line. To obtain user input and then print the result as output, we need to bring the IO input output library into scope. We need to bring the IO input output library into scope. The IO library comes from the standard library known as std. Okay, the IO library comes from the standard library. So by default, Rust has a set of items defined in the standard library that it brings into the scope of every program. This set is called the prelude, and you can see everything in it in the standard library documentation. So every Rust program has this prelude. Okay, that makes sense by default. If a type you wanna use isn't in the prelude, you have to bring that type into scope explicitly with the use statement like this, because this IO is not included in prelude in the standard library, so we have to use this use statement. And okay, so using the stdio library provides you with a number of useful features, including the ability to accept user input. As you saw in chapter 1, the main function is the entry point into the program. The main function. So the fn syntax declares a new function that the parentheses indicate there are no parameters, and the curly bracket starts the body of the function. As you also learned in chapter 1, println is a macro that prints a string to the screen. So guess the number println. Println is a macro that prints a string. Okay, yeah, chapter 1. So these are macros, and this code is printing a prompt stating what the game is and requesting input from the user, storing values with variables. Next, we will create a variable to store the user input like this. Let mute guess string new. Now the program is getting interesting. There's a lot going on in this little line. We use the let statement to create the variable. Here's another example. This line creates a new variable named apples and binds it to the value 5. In Rust, variables are immutable by default, meaning once we give the variable a value, the value won't change. We will be discussing this concept in detail in the variables and immutability section in chapter 3. To make a variable mutable, we add mute before the variable name. Let apples 5, let mute bananas 5, immutable and mutable. Note, / syntax starts a comment that continues until the end of the line. Rust ignores everything in comments. We will discuss comments in more detail in chapter 3. Returning to the guessing game program, you now know that let mute guess will introduce a mutable variable named guess. The equal sign tells Rust we wanna build something to the variable now. So returning to the guessing game program, you now know that let mute guess will introduce a mutable variable named guess. The equal sign tells Rust we wanna bind something to the variable now. Okay, so on the right of the equal sign is the value that guess is bound to, which is the result of calling string new, a function that returns a new instance of a string. String is a string type provided by the standard library that is growable. UTF-8 encoded a bit of text. String is a string type provided by the standard library that is growable. String is a string type provided by the standard library that is growable. It is provided by the standard library. So definitely this is like prelude. It is included in prelude. UTF-8 encoded bit of text. It's a UTF-8 encoded bit of text and global and provided by standard library. So the double colon syntax in the new line indicates the new is an associated function of the string type. An associated function is a function that's implemented on a type. Oh, so associated function is a function that is implemented in a type. Okay, so on a type, in this case string, this new function creates a new empty string. You will find a new function on many types because it's a common name for a function that makes a new value of some kind. It's a common name for a function that makes a new value of some kind. Okay. In full, the let mute guess string new line has created a mutable variable that is currently bound to a new empty instance of a string. This line has created a mutable variable that is currently bound to a new. Okay, has created a mutable variable that is currently bound to new. That is currently bound to a new. The mutable variable is bound to new associated function. Okay, so receiving user input, recall that we included the input-output functionality from the standard library with use stdio. Recall that we included the input-output functionality from the standard library with the use stdio. Recall that we included the I/O functionality from the standard library with the use stdio on the first line of the program. Now we will call the stdin function from the I/O module, which will allow us to handle user input. Recall that we included the input-output functionality from the standard library. We use stdio on the first line of the program. Okay. Now we call the stdin function that from the I/O module, which will allow us to handle user input. Okay. So this stdin function is coming from this I/O library, I/O module, and read a line. So if we hadn't imported the I/O library that uses stdio at the beginning of the program, we could still use the function by writing this function called as stdio stdin. The stdin function returns an instance of a stdio stdin, which is a type that represents a handle to the standard input for your terminal. Which is a type. This stdin returns a type that represents a handle to the standard input for your terminal. Next, the line, read a line here calls the read line method on the standard input handle to get input from user. We are also passing mute guess as the argument to read line to tell it what string to store the user input in. The full job of read line is to take whatever the user types into standard input and append that into a string without overriding its contents. So we therefore pass that string as an argument. The string argument needs to be mutable, so the method can change the string's content. Makes sense. So the here ampersand indicates that this argument is a reference, which gives you a way to let multiple parts of your code access one piece of data without needing to copy the data into memory multiple times, which gives you a way to let multiple parts of your code access one piece of data without needing to copy the data into memory multiple times. References. references are a complex feature, and one of Rust's major advantages is how safe and easy it is to use references. You don't need to know a lot of those details to finish this program for now. All you need to know is that, like variables, references are immutable by default. Hence, you need to write mut guess rather than guess to make it mutable. Chapter 4 will explain references more thoroughly, handling potential failure with the result type. We are still working on this line of code. We are now discussing a third line of text, but note that it is still part of a single logical line of code. The next part is this method, expect. We could have written this code as IOSTDIN readLine mut guess expect failed to read a line. However, one long line is difficult to read, so it's best to divide it. It's often wise to introduce a new line and other white space to help break up long lines when you call a method with the method name syntax. Now let's discuss what this line does. However, one long line difficult to read, it's such best divided. It's okay. So another white space to help break up long lines when you call a method with that method name syntax. Now let's discuss what this line does. As I mentioned earlier, read line puts whatever the user enters into the string we pass to it, but it also returns a result value. The read line returns a result value. Result is an enumeration, often called an enum, which is a type that can be in one of multiple possible states. Also, enum is a type that can be in one of multiple possible states. So it has a different states, but it can be one of different states. So we call each possible state a variant. So each possible state is a variant. Okay. So chapter 6 will cover enums in more detail. The purpose of these result types is to encode error handling information. Results variants are okay and error. Okay, so two variants there, two states. So the OK variant indicates the operation was successful, and inside OK is the successfully generated value. Successfully generated value. So OK variant indicates the operation was successful, and inside OK is the OK variant is the successfully generated value. The error variant means the operation failed, and error contains information about how or why the operation failed. Values of the result type, like values of any type, have methods defined on them. An instance of result has an expect method that you can call. So values of the result type, like values of any type, have methods defined on them. An instance of a result has an expect method. Okay. So an instance of result has an expect method that you can call. Okay, so that's good. So if this instance of a result is an error value, expected will cause the program to crash and display the message that you passed as an argument to expect. If the readLine method returns an error, it will likely be the result of an error coming from the underlying operating system. If this instance of a result is an OK value, expected will take the return value that okay is a holding and return just the value to you so you can use it. In this case, the value is the number of bytes in the user's input. If the instance of result is an OK value, expected will take the return value that OK is a holding. Okay, so expected will return the value that OK is a holding. Okay, so and return just that value to you so you can use it. In this case, the value is the number of bytes in the user's input. If you don't call expect, the program will compile, but you will get a warning. This result may be an error variant which should be handled. So Rust warns that you haven't used the result value returned from read line, indicating that the problem hasn't handled a possible error. The right way to suppress the warning is to actually write error handling build, but in our case we just wanna crash this program when a program occurs, so we can use expect. You will learn about recovering from errors in chapter 9. Printing values with the println placeholders. Aside from the closing curly bracket, there's only one more line to discuss in the code so far. The line prints the string that now contains the user's input. Wait a second. So also warns you that you haven't used the result value returned from read line. Indicating that the program has handled a possible error. The right way to suppress the warning is to actually write error handling. But in our case, we just want to crash this program when a program occurs, so we can use expect. You will learn about recovering from errors in chapter 9. Printing values. Printing values with println placeholders. Also, aside from the closing curly bracket here, there's only one more line to discuss. Discussed in the code so far. You guess. This line prints the string that now contains the user's input. The curly brackets set of curly brackets is a placeholder. Think of curly bracket as a little crab pincers that hold the value in place. You can print more than one value using curly brackets. The first set of curly brackets hold the first value listed after the format string. The second set holds the second value, and so on. Printing multiple values in one call to println macro would look like this. Printing multiple values in one call to println. Okay, so this code would print x equals 5 and y equals 10. Testing the first part. Let's test the first part of the guessing game. Run it using cargo run. At this point, the first part of the game is done. We are getting input from the keyboard and then printing it. At this point, the first part of the game is done. We are getting input from the keyboard and then printing it. Okay, 6, and then get 6. So generating a secret number. Next, we need to generate a secret number that the user will try to guess. The secret number should be different every time, so the game is fun to play more than once. We will use a random number between 1 and 100, so the game isn't too difficult. Rust doesn't yet include a random number functionality in its standard library. However, the Rust team does provide a random crate with said functionality. Next, we need to generate a secret number that the user will try to guess. The secret number should be different every time, so the game is fun to play more than once. We will use a random number between 1 and 100, so the game isn't too difficult. Rust doesn't yet include a random number. And the functionality in its standard library. However, the Rust team does provide a random crate with a set functionality. Random number functionalities doesn't yet include the random number functionality in the standard library. Okay, so using a crate to get more functionality. Remember that a crate is a collection of Rust source code files. The project we've been building is a binary crate, which is an executable. Remember that a crate is a collection of Rust source code files. So it is a group of multiple Rust files. So the project we've been building is a binary crate. Which is an executable. The random crate is a library crate. So there is an executable crate, there is a binary crate and library crate. Okay, so which contains code intended to be used in other programs and can't be executed on its own. Random crate is a library crate which contains code intended to be used in other programs and can't be executed on its own. Okay, makes sense. So Cargo's coordination of external crate is where Cargo really shines. Before we can write code that uses rand, we need to modify the cargo.toml file to include the rand crate as a dependency. Open the file now and add the following line to the bottom beneath dependencies section header that Cargo created for you. Be sure to specify rand exactly as we have here. With this version number or the code examples in this tutorial may not work. In the cargo.toml file, everything that follows a header is a part of that section that continues until another section starts. In the cargo.toml file, everything that follows a header is part of the section that continues until another section starts. In dependencies, you tell Cargo which external crates in dependencies, you tell Cargo which external crates your project depends on. And which versions of those crates you require. In this case, we specify the rand. In this case, we specify the rand crate with the semantic version specifier. Okay, so we specify the rand crate with the semantic. Okay, so Cargo understands the semantic versioning, sometimes called semver, which is a standard for writing version numbers. The number is actually shorthand for which means any version that at least but below. Oh, which means any version that is at least okay, at least but below. Okay, makes sense. So 0.8. Cargo considers these versions to have public APIs. Cargo considers these versions to have public APIs. To have public APIs compatible with version 0.8. Cargo considers these versions to have public APIs compatible. And this specification ensures you will get the latest patch release that will still compile with the code in this chapter. And this specification ensures you will get the latest patch release that will still compile code in this chapter. Any version or greater is not guaranteed to have the same API as the what following examples use. Now, without changing any of the code, let's build the project as shown in listing 2-2. Listing 2-2, the output from running cargo build after adding the rand crate as a dependency. You may see different version numbers, but they will all be compatible with the code, thanks to the Semver. Different lines depending on the operating system, and the lines may be in a different order. When we include an external dependency, wait a second. So cargo build and then updating, download the rand and something like okay, different things inside the render dependencies, render crate, and compiling is in game. Okay, so you may see different version numbers, but they will be all be compatible with the code, thanks to Semver. Different lines depending on the operating system, and the lines may be in a different order. When we include an external dependency, Cargo fetches the latest versions of everything that dependency needs from the registry. Cargo fetches the latest versions of everything. Cargo fetches the latest versions of everything that dependency needs from the registry, which is a copy of data from crates.io. Crates.io is where people in the Rust ecosystem post their open source Rust projects for others to use. Wait a second. When we include an external dependency, Cargo fetches the latest versions of everything. Okay. The latest versions of everything that dependency needs from the registry, which is a copy of data from crates.io. So crates.io, okay. Crates.io is where people in the Rust ecosystem post their open source Rust projects for others to use. Crates.io is where people Crates.io is where people in the Rust ecosystem post their open source Rust projects for others to use. Cargo.io is where people in the Rust ecosystem post their open source Rust projects for others to use. After updating the registry, Cargo checks the dependency section and downloads any crates listed that aren't already downloaded. In this case, although we only listed rand as a dependency, Cargo also grabbed the other crates that rand depends on to work. After downloading the crates, Rust compiles them and then compiles the project with the dependencies available. After updating the registry, cargo checks the dependencies section and downloads any crates listed that aren't already downloaded. Although we only received rand as a dependency, cargo also grabbed the other crates that rand depends on to work. After downloading the crates, Rust compiles them and then compiles the project with the dependencies available. If you immediately run cargo build again without making any changes, you won't get any output aside from the finished line. Cargo knows if you immediately run cargo build again without making any changes, you won't get any output aside from the finished line. Cargo knows it has already downloaded and compiled the dependencies, and you haven't changed anything about them in your cargo.toml file. Cargo also knows that you haven't changed anything about your code, so it doesn't recompile that either. With nothing to do, it simply exists. So if there is no change on my code in my code, and cargo build doesn't compile my code, and also if the dependencies are the same thing, it is already downloaded, everything is downloaded, then cargo build will not download crates dependencies. So if you open the src main.rs file, make a trivial change and then save it and build it again, you will only see the 2 lines of output. These lines show cargo only updates the build with your tiny change to the src/main.rs file. These lines show cargo only updates the build with your tiny change. If you want to make a trivial change and then save it and build again, you will only see 2 lines of output. Click the compile and cascade. Finished. These lines show cargo only updates the build with your tiny change to the src main.rs file. Your dependencies haven't changed, so cargo knows it can reuse what if has already downloaded and compiled for those. These lines show cargo only updates the build with your tiny change. So cargo, if I update my code and cargo doesn't update dependencies, okay. If dependencies are same, okay. It's because it already downloaded and compiled for those. Ensuring reproducible builds with the cargo.log file. Cargo has a mechanism that ensures you can rebuild the same artifact. Ensuring reproducible builds with the cargo.log file. Ensuring reproducible builds with cargo.log file. Cargo has a mechanism that ensures you can rebuild the same artifact every time you or anyone else builds your code. Cargo will use only the versions of the dependencies you specified until you indicate otherwise. Cargo will use only the versions of dependencies you specified until you indicate otherwise. Yes. So for example, say that next week version 8.084 of the rand crate comes out, and that version contains an important bug fix, but it also contains a regression that will break your code. To handle this, Rust creates the cargo.log file the first time you run cargo build. So we now have this in the guessing game directory. Cargo.log file the first time you run cargo build. So when I run my cargo build the first time on the program, then it creates a cargo.log file. Okay. When you build a project for the first time, Cargo figures out all the versions of the dependencies that fit the criteria and then writes them to the cargo.log file. When you build your project in the future, Cargo will see that the cargo.log file exists and use the version specified there rather than doing all the work of figuring out versions again. This lets you have a reproducible build automatically. Wait a second. So when you build a project for the first time, Cargo figures out all the versions of the dependencies that fit the criteria and then writes them to the cargo.log file. When you build your project in the future, Cargo will see that the cargo.log file exists and use the version specified there rather than doing all the work of figuring out versions again. This lets you have a reproducible build automatically. When you build a project for the first time, Cargo figures out all the versions of the dependencies. When you build a project for the first time, Cargo figures out all the versions of the dependencies. When you build a project for the first time, Cargo figures out all the versions of the dependencies. And then fit the criteria and then write them to the cargo.log file. When you build your project in the future, you will see that the cargo.log file exists and use the version specified there rather than doing all the work of figuring out versions again. Use the version specified rather than doing all the work of figuring out versions again. Okay. So only first time. Okay. This lets you have a reproducible build automatically. In other words, your project will remain at 0.8.3 until you explicitly upgrade, thanks to the cargo.log file. Because the cargo.log file is important for reproducible builds, it's often checked into source control with the rest of the code in your project. Updating a create. Wait a second. Because the cargo.log file is important to reproducible builds, it's often checked into source control with the rest of the code in your project. I don't know what that. Let me see. Okay. So updating a crate to get a new version. When you do want to update a crate, updating a crate to get a new version. When you do wanna update a crate, Cargo provides the command update. When you do wanna update a crate, Cargo provides the command update. Okay, so which will ignore the cargo.log file and figure out all the latest versions that fit your specifications in cargo.toml. Cargo will then write those versions to the cargo.log file. Otherwise, by default, Cargo will only look for versions greater than 0.83 and less than 0.90. If the render crate has released the two new versions 084 and 090, you would see the following if you ran cargo update. If the render crate has released the two new versions and 0.8, 084, 090, you do see the following if you ran cargo update. You do see the following if you ran cargo update. If the render crate has released the two new versions 084 and 090, you do see the following if you ran cargo update. Cargo ignores the 090 release. At this point, you do also notice a change in your cargo.log file, noting that the version of the render crate you are now using 084 to use a render version 090 or any version in the 09x series. You do have to update the cargo.toml file to look like this thread instead. Cargo ignores the 090 release. At this point, you would also notice a change in your cargo.log file, noting that the version of the render crate you are now using is 084. Cargo ignores the release. At this point, you would also notice a change in your cargo.log file, noting that the version of the render crate you are now is to use your render version or any version in the series. You would have to update cargo.toml file to look like this instead. Okay. So even though I use cargo update command, it won't it will be restricted to the by the same some yeah, what is it? Yeah, Semver, semantic versioning. Okay. Okay, that makes sense. To use your render version or any version in the 09 series. Okay. So the next time you run cargo build, cargo will update the registry of crates available and reevaluate your render requirements according to the new version you have specified. There's a lot more to say about cargo and its ecosystem, which we will discuss in chapter 14, but for now, that's all you need to know. Cargo makes it very easy to reuse your libraries, so Rustaceans are able to write smaller projects that are assembled from a number of packages. For now, that's all you need to know. Cargo makes it very easy to reuse your libraries, so Rustaceans are able to write smaller projects that are assembled from a number of packages. Okay, so generating a random number. Let's start using rand to generate a number to guess. The next step is to update src main.rs as shown in listing 2-3. Listing 2-3 adding code to generate a random number. First, we add the line use rand rng. The rng trait defines method that random number generators implement, and this trait must be in scope for us to use those methods. Chapter 10 will cover traits in detail. Oh, so there's okay, secret number, rand rand create rng rand. So first we add the line user rand rng the rng trait defines this is a trait. So rng trait defines the methods that random number generators implement. And this trait must be in scope for use of those X methods. And this trait must be in scope for us to use those methods. Chapter 10 will cover traits in detail. And this trait must be in scope for us to use those methods. Chapter 10 will cover traits in detail. Okay, so next we adding 2 lines in the middle. Next we are adding 2 lines in the middle. Next we are adding 2 lines in the middle. In the first line we call rand thread rng function that gives us the particular random number generator that we are going to use. Function that gives us the particular random number generator that we are going to use. One that is local to the current thread of execution and seeded by the operating system. Next we are adding 2 lines. Okay. The thread rng function that gives us the particular random number generator that we are going to use, one that is local to the current thread of execution and seeded by the operating system. Then we call the genRange method on the random number generator. This method is defined by the rng trait that we brought into scope with the user rand rng statement. The genRange method takes a range expression as an argument and generates a random number in the range. The kind of range expression we are using here takes the form start to end and is inclusive on the lower and upper bounds. So we need to specify to request number between 1 and 100. The kind of range expression we are using here takes the form start to end is inclusive on the lower and upper bounds. This method is defined by the rng trait. Okay, so wait a second. Function that gives us the particular random number generator. Function that gives us the particular random number generator that we are going to use, one that is local to the current thread of execution and seeded by the operating system. One that is local to the current thread of execution and seeded by the operating system. Then we call the genRange. This part is difficult. So then we call the genRange method on the random number generator. This method is defined by the rng trait that we brought. This method is defined by the rng trait that we brought into scope with the user rand rng statement. The genRange method takes a range expression as an argument and generates a random number in the range. The kind of range expression we are using here takes you the form set and is inclusive on the lower and upper bounds. So we need to specify 1 to 100 to represent to request a number between 1 and 100. Wait a second. So this is by the processing. Then we call the gen range method on the random number. Random number generator. This method is defined by the RNG trait that we brought gen range. Okay. Random number generator. This method is defined by the RNG trait. Okay. That we brought into scope with the user and the RNG statement. The gen range method takes a range expression as an argument and generates a random number in the range. The kind of range expression we are using here takes it's inclusive and the start and it's inclusive on the lower and upper bounds. So we need to specify Note, you won't just know which traits to use and which methods and functions to call from create. So each crate has a documentation with instructions for using it. Another neat feature of Cargo is that running the Cargo doc open command will build the documentation provided by all of your dependencies locally and open it in your browser. If you are interested in other functionality in the render crate, for example, Cargo doc open and click render in the sidebar on the left. The second new line prints the secret number. This is useful while we are developing the program to be able to test it, but we will delete it from the final version. It's not much of a game if the program prints the answer as soon as it starts. The second new line prints the secret number. 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 Makes sense. Wait a second, what? You won't just know which traits to use and which methods and functions to call from a crate. You just won't just know which trait to use and which methods and functions to call from a crate. Okay, so each crate has a documentation with instructions for using it. So each crate has a documentation and instructions for using it. Another neat feature of Cargo is that running Cargo doc open command will build the documentation provided by all of your dependencies locally and open it in your browser. If you are interested in other functionality in the render crate, for example, run Cargo doc open and click render in the sidebar on the left. Okay. The second new line prints the secret number. The second new line prints the secret number. This is useful while we are developing the program to be able to test it, but we will delete it from the final version. It's not much of a game if the program prints the answer as soon as it starts. The second new line prints the secret number. The second new line prints the secret number. The second new line print is the secret number. This is useful while we are developing the program to be able to test it. The second it's not much of a game if the program prints the answer as soon as it starts. Try running the program a few times. Cargo run, compiling, guessing game, and blah blah blah. Guess the number. The secret number is 7. Please input your guess. You guessed 4. Cargo run. Finish the dev. Unoptimized debug targets in 0.02 seconds. Running target debug guessing game. Guess the number. The secret number is 83. Please input your guess. 5. You guessed 5. You should get different random numbers and they should all be numbers between 1 and 100. Great job. Comparing the guess to the secret number. Now that we have a user input and a random number, we can compare them. The step is shown in listing 2-4. Note that this code won't compile quite yet, as we will explain. Comparing the guess to the secret number. Now that we have user input a random number, we can compare them. The step is shown in listing 2-4. Note that this code won't compile quite yet, as we will explain. That step is shown in listing 2-4. Note that this code won't compile quite yet, as we will explain. Listing 2-4. Handling the possible return values of comparing two numbers. Listing 2-4. Handling the possible return values of comparing two numbers. First, we add another user statement bringing a type called std_cmp ordering into scope from the standard library. The ordering type is another enum and has the variance less greater and equal. These are the 3 outcomes that are possible when you compare two values. When we add 5 new lines at the bottom that use the ordering type, the CMP method compares. Oh my god, so wow, this is cool. Pairing secret number. Second, you print line the right of your line. You should get different random numbers and they should all be numbers between 100. Comparing the guess the secret number. Comparing the guess to the secret number. Now that we have user input and a random number, we can compare them. That step is shown in listing 2-4. Note that this code won't compile quite yet, as we will explain. First, we add another user statement bringing a type called std_cmp ordering. First, we add another user statement. Bringing a type called std_cmp ordering into scope from the library. Ordering type. The ordering type is another enum and has the variance less greater and equal. Oh, this is also enum type. Okay. These are the 3 outcomes that are possible when you compare two values. these are the three outcomes. These are the three outcomes that are possible when you compare two values. These are the three outcomes that are possible when you compare two values. Okay, these are the three outcomes that are possible when you compare two values. True. So then we add 5 new lines at the bottom that you use the ordering type. The CMP method compares CMP method. The CMP method compares two values okay. The CMP method compares two values and can be called on anything that can be compared. It takes a reference to whatever you wanna compare with. Here it's comparing the guess to the secret number. It's comparing the guess to the secret number. Then it returns a variant of the ordering. Variant of the ordering. Okay, variant of the ordering. Oh. So if I use CMP ordering, okay, so okay, that makes sense. CMP method returns the variant of the ordering type. Okay, makes sense. Type. Okay. Then it returns the variant of ordering. Okay, makes sense. So whatever you wanna compare with. Here it's comparing the guess to the secret number. Then it returns a variant of the ordering enum we brought into scope with the use statement. We use a match expression to decide what to do next based on which variant of ordering was returned from the call to CMP with the values in guess and secret number. Then returns the variant of the enum. Variant of the ordering enum we brought into the scope with the use statement. We use a match expression to decide what to do next based on which variant of ordering was returned from the call to CMP with the values in guess and secret number. A match expression is made up of arms. An arm consists of a pattern to match against, and the code that should be run if the value given to match, and the code that should be run in if the value given to match fits the arms pattern. If the value given to match fits the arms pattern. Okay. Rust takes the value given to match and looks through each arms pattern in turn. Patterns and the match construct are powerful. Rust features that let you express a variety of situations your code might encounter and make sure that you handle them all. These features will be covered in detail in Chapter 6 and Chapter 18 respectively. Rust takes a value given to the match and looks through each arms pattern in turn. Patterns and the match constructed are powerful. Rust features that let you express a variety of situations your code might encounter and make sure that you handle them all. These features will be covered in detail in Chapter 6 and Chapter 18 respectively. Difficult. The first time, Rust takes a value given to match and looks through each arms pattern in turn. Patterns and the match constructed are powerful. Rust feature that let you express a variety of situations your code might encounter and make sure that you handle them all. These features will be covered in detail. Okay, makes sense. So let's walk through an example with the match expression we use here. Say that the user has guessed 50. and the randomly graded secret. Let's walk through an example. Watch the match expression we use here. Let's walk through an example with the match expression we use here. Say that the user has guessed 50 and the randomly generated secret number this time is 38. Say that the user has guessed 50. Say that the user has guessed 50 and the randomly generated secret number in this time is 38. When the code compares 50 to 38, the CMP method will return ordering greater because 50 is greater than 38. Say that the user has guessed 50. Say that the user has guessed 50 and randomly. Say that the user has randomly 50 and the randomly generated secret number this time is 38. Let's walk through an example with the match expression we use here. Say that the user has guessed 50. Let's walk through an example with the match expression we use here. Oh my god. Say that the user has guessed 50 and the randomly generated secret number this time is 38. When the code compares 50 to 38. The CMP method will return ordering greater. Yeah, because 50 was like input, so guess.cmp, so yes, guess is greater. Guess is the greater than 38. The match expression gets the ordering greater. The match expression gets the ordering greater value and start checking each arms pattern. It looks at the first arms pattern ordering less and sees that the value ordering greater does not match ordering less. So it ignores the code in the arm and moves to the next arm. The next arm's pattern is ordering greater, which doesn't match ordering greater. The associated code in that arm will execute and print too big to the screen. That match expression ends after the first successful match, so it won't look at the last arm in this scenario. However, the code in listing 2-4 won't compile yet. Let's try it. Expected structed string found integer. So wait a second, let me see. See that the value ordering greater does not match ordering less, so it ignores the code. Okay, returns the greater. It ignores the code in that arm and moves to the next arm. The next arm pattern in ordering greater, which does match ordering greater. The associated code in that arm will execute and print too big to the screen. The match expression ends after the first successful match, so it won't look at the last arm in this scenario. The core of the error states that there are mismatched types. The core of the error states that there are mismatched types. The core of the error says that there are mismatched types yet. Oh, what the fuck? Expected structed string found the integer. The core of the error. Rust has a strong static type system, however it also has a type inference. When we wrote let must mute guess string new, Rust was able to infer that guess should be a string and didn't make us write at the time. The secret number on the other hand is number type. Right. A few of Rust's number types can have a value between 1 and 100. I32 or 32 bits. Rust number types can have a value between 1 and 100. U32 as well as others, unless otherwise specified. The Rust defaults to an I32. Unless otherwise specified, the Rust defaults to an I32. Unless you add type information elsewhere that would cause Rust to infer a different numerical type. The reason for the error is that Rust cannot compare a string and a number type. Ultimately, we wanna convert the string the program reads as input into a real number type so we can compare it numerically and the secret number. So Rust defaults an I32, which is a type of secret number, unless you add a type information elsewhere that would cause Rust to infer a different numerical type. The reason for the error that Rust cannot compare a string and a number type. Ultimately, we wanna convert the string the program reads as input into a real number type so we can compare it numerically. So the secret number, we do so by adding this line to the main function body. Ultimately, we want to convert the number so we can compare it numerically to the secret number. So we do so by adding this line to the main function body. Okay. So respect to stream parse expect here. Come on. Oh, here's right, guess. Yes, guess here. Stream parse, okay. We created a variable named guess, but wait, doesn't the program already have a variable named guess? It does, but helpfully, Rust allows us to shadow the previous value of guess with a new one. Shadowing lets us reuse the guess variable name rather than forcing us to create two unique variables. We create a variable named guess. But wait, doesn't the program already have a variable named guess? It does, but helpfully Rust allows us to shadow the previous value. It does, but helpfully Rust allows us to shadow. It does, but helpfully Rust allows us to shadow the previous value of a guess with a new one. It does, but helpfully Rust allows us to shadow the previous value of a guess with a new one. It does, but helpfully, Rust allows us to shadow a previous value of guess with a new one. Shadowing lets us reuse the guess variable name rather than forcing us to create two unique variables. Reuse the guess variable name. Okay. Such as guess, str, and guess, for example. We will cover this in more detail in chapter 3, but for now, know that this feature is often used when you wanna convert a value from one type to another type. But for now, know that this feature is often used when you wanna convert a value from one type to another type. Okay. We bind this new variable to the expression. Guess trim parse. The guess in the expression refers to the original guess variable that contained the input as a string. We bind this new variable to the expression guess trim parse. The guess in the expression refers to the original guess variable that contained the input as a string. We'll cover this in more detail in chapter 3, but for now, we bind this new variable to the expression guess trim parse. The guess in the expression refers to the original guess variable. The guess in the expression refers to the original guess variable that contained the input as a string. The trim method on the string instance will eliminate any white space at the beginning and end. Which we must do to be able to compare the string into the U32, which can only contain numerical data. The user must press enter to satisfy a read line and input their guess, which adds a new line character to the string. For example, if the user type 5 and press enter, guess looks like this: 5 reverse the slash e and reverse the slash e and represent this new line. On Windows, pressing enter results in a character return and a white line. The trim method eliminates n and rn, resulting in just 5. The parse method on strings converts a string to another type. Here we use it to another type from a string to number. We need to tell Rust the exact number type we want by using letGuess U32. The colon after guess tells Rust we will annotate the variable's type. Rust has a few built-in number types. The U32 seen here is an unsigned. The 32-bit integer is a good default choice for a small positive number. You will learn about other number types in chapter 3. Additionally, the U32 notation in this example program and the comparison with secret number means that Rust will infer that secret number should be a U32 as well. So now the comparison will be between two values of the same type. Rust has a few built-in number types. The U32 see here is an unsigned 32-bit integer. It's a good default choice for a small positive number. You will learn about the Rust has a few built-in number types. The U32 seen here is an unsigned 32-bit integer. It's a good default choice for a small positive number. You will learn about other number types in chapter 3. Additionally, the U32 annotation in this example program on the comparison with a secret number means that roster will infer that secret number should be U32 as well. So now the comparison will be between two values of the same type. The roster will infer the secret. Wait a second. Additionally, the 33 indentation in this example program comparison with secret number means that roster will infer the secret number should be 32 as well. So now the comparison will be between two values of the same type. Is what is that secret number? Parse method will only work on characters that can logically be converted into numbers. The parse method will only work on characters that can logically be converted into numbers and so can easily cause errors. If, for example, the string contains there would be no way to convert it to number because it might fail. The parse method returns the result type, but as much as the readLine method does discussed earlier in handling potential failure with result type. Because it might fail, the parse method returns the result type much as the readLine method does. We'll treat this result the same way by using the expected method again. We will treat this result as the same way by using the expected method again. If a parse returns an error result variant because it could create a number from the string, the expected call will crash the game and print the message we give it. If a parse can successfully convert the string to a number, it will return the OK variant of a result, and expected will return the number that we want from the OK value. Let's run the program now. Nice! Even though spaces were added before the guess, the program still figured out that the user guessed 76. Run the program a few times to verify the different behavior with different kinds of input. Guess the number correctly. Guess a number that is too high, and guess a number that is too low. Nice, even though spaces were added before the guess. Nice, even though spaces were added. Nice, even though spaces were added. Nice, even though spaces were added before the guess. Nice, even though spaces were added. Nice, even though spaces were added before the guess. Nice, even the spaces were added before the guess. The program still figured out that the user guessed the 76, run the program a few times to verify different behavior with different kinds of input. Run the program a few times to verify correctly. Guess a number that is too high and guess too low. We have most of the game working now, but the user can make only one guess. Let's change it by adding a loop, allowing multiple guesses with looping. The loop keyword creates an infinite loop. We will add a loop to give users more chances at guessing the number. Allowing multiple guesses with looping. The loop keyword creates an infinite loop. We will add a loop to give users more chances at guessing the number. The secret number is secret number. Please input your guess. The loop keyword creates an infinite loop. We will add a loop to give user more chances to guess. Okay. So loop here. Okay. As you can see, we've moved everything from the guess input from the prompt onward into a loop. As you can see, we've moved everything from the guess input prompt onward into a loop. As you can see, we've moved everything from the guess. As you can see, we've moved everything from the guess input prompt onward into a loop. As you can see, we've moved everything from the guess. Okay, so input prompt, the guess from the input prompt onward into. Be sure to indent the lines inside the loop another 4 spaces, switch and run the program again. The program will now ask for another guess forever, which actually introduces a new problem. It doesn't seem like the user can quit. The user could always interrupt the program by using the keyboard shortcut Ctrl+C, but there's another way to escape this insatiable monster. As mentioned, insatiable. As I mentioned in the parse, because in comparing the guess to the secret number. As I mentioned in the parse discussion, in comparing the guess to the secret number. As you mentioned in the parts discussion in comparing the guess to the secret number, if the user enters a non-number answer, the program will crash. We can take advantage of that to allow the user to quit, as shown here. If the user enters a non-number answer, the program will crash. We can take advantage of that to allow the user to quit, as shown here. Try and quit will quit the game, but as we will notice, so we're entering and not any other non-type number input. This is suboptimal to say the least. We want the game to also stop when the correct number is guessed. Quitting after a correct guess. After a correct guess. Let's program the game to quit when the user wins by adding a break statement. Quitting after a correct guess. Let's program the game to quit when the user wins by adding a break statement, or not break. So adding the break line after you win makes the program exit the loop when the user guesses the secret number correctly. Exiting the loop also means exiting the program, because the loop is the last part of the main. Handling invalid input. To further refine the game's behavior, rather than crashing the program when the user inputs a non-number, let's make the game ignore a non-number so the user can continue guessing. We can do that by altering the line. Refine game's behavior rather than crashing the program when the user inputs a non-number. Let's make the game ignore a non-number so the user can continue guessing. We can do that by altering the line where guess is converted from a string to U3, as shown in listing 2-5. To further refine the game's behavior rather than crashing the program, handling invalid input. To further refine the game's behavior rather than crashing the program when the user inputs a number. Rather than crashing the program when the user inputs a number. Let's make the game ignore a non-number so the user can continue guessing. We can do that by altering the line where guess is converted from a string to AU32, as shown in listing 2-5. We switch it from an expected call to a match expression. We switch it from an expect to call to a match expression. Okay, match. Okay, that makes sense because it returns result. Okay. Result is an enum that has the variance of OK and error. We are using a match expression here as we did with the ordering result of the CMP method. If a parse is able to successfully turn the string into a number, if let's say if parse is able to successfully turn the string into a number, it will return an OK value that contains the resulting number. Parse is able to successfully turn the string into a number. If parse is not able to turn the string into a number, it will return an error value that contains more information about the error. The error value does not match the OK num pattern in the first match arm, but it doesn't match the error pattern in the second arm. But it doesn't match the error pattern in the second arm. After the underscore. The score is catch all value. In this example, we are saying we wanna match all error values. In this example, we are saying we want to match all error values, no matter what information they have inside them. Program will execute to the second arm's code. So the program will execute to the second arm's code. Continue, which tells the program. Program will execute the second arm's code and continue, which tells the program to go to the next iteration of the loop and ask for another guess. So effectively, the program ignores all errors that parse might encounter. Now everything in the program should work as expected. Let's try it. Awesome. Please input your guess. Awesome. Okay, recall the program is still running the secret number that worked for the default action, but it runs the game. Let's delete the println that outputs the secret number. Summary: at this point, you successfully built the guessing game. Congratulations. This project was a hands-on way to introduce you to many new Rust concepts. Let match, functions, the use of external crates, and more. In the next few chapters, you will learn about these concepts in more detail. Chapter 3 covers concepts that most programming languages have, such as variable data types and functions, and shows how to use them in Rust. Chapter 4 explores ownership, a feature that makes Rust different from other languages. Chapter 5 discusses structures and method syntax, and Chapter 6 explains how enums work. Let match, functions, use of external crates, and more. In the next new chapters, you will learn about these concepts in more detail. Chapter 3 covers concepts. Chapter 3 covers concepts that most programming languages have, such as variables, data types, and functions, and shows how to use them in Rust. Chapter 4 explores ownership, a feature that makes Rust different from another language. Chapter 5 discusses structures and method syntax, and Chapter 6 will explain how enums work.